So, in continuation to this optical isomerism, so let us take one word called a racemic mixture. This is a mixture of the two optical isomers, 1:1 ratio of D and L compounds. This 1:1 ratio may be either by taking the equal amounts of by weight or by volume or by number also you can count and then mix. The optical activity of such a mixture will be the 0. This is called because of the one compound produces, let us say, -25, the other one produces +25, therefore it is cancelled and the net optical activity of such isomers will be the net will be the 0. And this is called also external compensation. External compensation. There is another example where a compound containing the two chiral centers, as we have seen in the case of the tartaric acid, has got a particular isomer wherein there is a two chiral centers 1 and 2 and it get cancelled. So, one chiral carbon what it produces is understood to cancel the second one. So, net optical isomerism of this particular compound is called also mesotartaric acid, whose optical isomerism is also 0. This is called internal compensation. This is called internal compensation. So, in the within the molecule cancellation is taking place, therefore, we call it as a internal compensation. There can be another example like CH3COOH, whose optical activity is also 0. This is because of the non-chirality, or the molecule is said to be achiral. There is no chiral nature at all. So, therefore, this compound is optically inactive, achiral or optically inactive. So, there are 3 zeros are there. 1 0 is in general most of the compounds where there is no chiral carbon, optical activity will be 0. There may be sometimes chiral carbons are there in the compound, but internal compensation leads to 0. Sometimes a mixture may have an equal amount, so therefore, compensation is external. One compound virtually cancelling the optical activity of the other one, therefore, it is called external compensation. Whenever this external compensation or racemic mixture is there, it can be separated into the two fractions. Separation can be done to get the two fractions. One is pure dextro compound and other one is pure levo compound. It is also observable point 1. What method you apply to separate? For example, the size of the molecules are different, you can go for the centrifugation and so on. If the molecules are one is magnetic, other one non-magnetic, a magnetic iron belt is used. Like that, you have already exposed with a huge number of methods of separation by crystallization, distillation and so on, based on the one of the physical point constant difference. Now, here as we have seen, the optical isomers will have almost all the properties, especially the boiling point, melting point, refraction indices, all such physical properties are the same. In such a case, then what property you make use to separate is again a problem. But still we have some procedures are there, we will see that separate issue. But the separation of racemic mixture is known as resolution. Resolution means it is a separation of racemic mixture into the pure D, pure D. If both you take and prepare a racemic mixture, that is called racemization. It is a mechanical racemization. Take X and Y, mix it. That is called reverse is called racemization. Get a mixture, mix it and get the mixture. So you get a mixture. This process of preparation of a DL mixture is known as racemization. But the racemization need not to be this type of the mixing the D and L. You too can get in some other way, like for example, when you are taking a compound like 2-iodobutane. We have a question also in the IIT JEE like this. 2-iodobutane is also called as secondary butyl iodide. There is a chiral carbon is there. Let us mark this carbon is chiral. So it shows optical activity. Let us show it's a dextro compound is there. A pure dextro compound I have taken. This dextro compound on heating with a solvent like acetone, actually it is enough to get a racemization, but he has taken a potassium iodide also and then heated. The I minus will go out. It's an alkyl iodide, therefore a part of the alkyl iodide. The 2-iodine has got outgoing property also better, so therefore it undergoes and it gives a carbocation. That results in the DL mixture. So he says write the good explanation or show the mechanism. So when I minus goes out, what you will get is a carbocation is formed. The carbocation will have a trigonal planarity. So 3 sides, 3 groups will be there. So in such a case, what is happening? The carbocation will have now a chance of I minus attacking from the upper side or from the lower side, giving the D and L 2 types of the mixture equally, because mathematically the trigonal planarity will have a 2 chances equal. So therefore D as well as L. I have taken dextro only, but dextro and levo both compounds are coming because the ionization of the alkyl iodide gives a non-chiral molecule, that is intermediate species carbocation is a planar one. Therefore it is giving this type of the mixture formation. This is not mechanical, this is a chemical method. Like alcohols, when you heat it, OH will come out carbocation. Once again water when you add, you will get back the alcohol. If you do dehydration, that is elimination reaction, but it can get back the original compound, but with the dextro-levo formation through the free radicals or carbocations, leading to give the mixtures. Though you take a pure compound, you get a mixture. This is called what? Racemization. This is a chemical racemization, getting a mixture from the either mixing or by the single compound taking. You too can get a mixture when you take a compound like acetaldehyde, for example. Acetaldehyde, if I add HCN, this is an addition reaction. The plus is added, the cyanide is added, a nucleophilic addition leads to give the chiral carbon OH and a cyanide and a hydrogen. There is a chiral carbon. Because this is a plane, the cyanide can approach in the both the ways. Therefore, you are going to get the D as well as L. This is from a non-chiral compound. We are getting a DL mixture. Probably many times you get a mixture, but there are some cases where the approach of the stereochemistry of this carbon, if it is hydrogens, I think you will get same. But instead of that, here we have a large and middle and the big groups. The always the nucleophile adds from the least or the smaller group side, giving the one of the isomer more, that is unequal quantities may be arisen also. But when all these are hydrogens, you will get the dextro-levo equal amount, leading to give the racemic mixture. This is not the racemization, it is called asymmetric synthesis. In the preparation of an asymmetric carbon, obviously we find many times a DL mixture formation, isn't it? So this is not the racemization. However, it is called the asymmetric synthesis. We are synthesizing a new chiral carbon. Previously it was there already, you are not going to create a chiral carbon, it was there and again you are getting. That's called actually racemization. Let us see some methods for the resolution, methods of resolution. As I said, resolution means a separation of a mixture, DL mixture. Mixture I am taking and we are separating into the pure D and the pure L. This is called what? The separation of racemic mixture is known as resolution. This can be done in different methods. One of the simple method is by hand picking. In this method, it's not applicable for all the compounds. Only certain compounds will give a beautiful crystals. Like for example, one crystal has got this particular model, and another crystal, its D compound if it is having, fortunately its isomer, I may not draw exactly, but it will be like this. So it will be a mirror image of this one. Even the crystal of the D will be a mirror image of the L compound. In such cases, with your either with naked eye or with the magnifying lens, you can see the crystal and separate, just like right-handed shells and the left-handed shells are mixed and given to you. Obviously, you can go on with hand, you can separate. Like that, if the crystals are so big, and that too, the molecule should have a one special property. When the D compound is crystallizing, L should not enter into that. So there are some compounds which do enter also, but we should have a not entering type of the compounds, and in such a case the method is perfectly okay. So make them crystals. Mixture you take, prepare the crystals. So D will come out as a one type of crystals, and L will come out as another type of crystal, which is a mirror image of this one. You separate them. So take the solution, prepare the crystals. Then in the form of crystals, you separate them and dissolve in a suitable solvent to get the solution, or pure solid you can get. So first of all, the molecule should have a crystallizing property. Common salt has got a better crystallizing when compared with the sugar. Sugar only under low atmospheric pressure and so many certain factors, then only you will get the crystal. Otherwise, lot of sugar is being wasted in the molasses, you know. So that is because of the non-crystallizing property of the sugar. Once sugar you dissolve in water and keep it in the sun, you won't get the crystals. You will get a gummy material. Perhaps this jaggery may be prepared, but not the crystals of the sucrose, isn't it? Like that, some molecule should have a capability of getting the crystals, that too visible crystals. Okay, so then the method is applicable, and it is a slow process and all that. So another method is there. This is called biological method. As I said, biologically the enzymes have got this discrimination. One particular enzyme is able to hydrolyze or react with one isomer, the same enzyme will not. In such a case, in the case here, there is one ammonium tartarate. Ammonium tartarate. This you take as a plus compound as well as minus compound. Both you have taken a mixture of ammonium tartarate, tartaric acid, salt of ammonia. So ammonium tartarate plus minus if you take, add the gram positive bacteria. Gram positive bacteria. This particular bacteria has got an enzyme maybe, and that enzyme will be able to oxidize the ammonium tartarate and get some energy, and it lives, it grows by consuming the plus ammonium tartarate only. What happened after certain time, only minus I is left over, minus ammonium tartarate is left over. So plus is by consumed by this one. This is in fact in one way it is no more separation. Where is the D? The dextro is gone, isn't it? Only minus is coming. So you have to choose another bacteria which eats away minus and then prepare a dye. So this is actually not a, basically not a separation means both I should get into my hand. This one we are losing, isn't it? So a lot of research has to do that. which bacteria or which biological system is effective towards the D or L. So therefore, one you are losing, and it is a very slow process, and so many drawbacks are there. But however, there is one method introduced by the Louis Pasteur, age old method, but hats off to him. Still we are now implementing this particular method in addition to the latest methods, however. But this method is introduced by the Louis Pasteur, and the method is called DL is converted into the diastereomers. In the form of diastereomers, you separate the two fractions x and y, then back convert into the D, and y gives the L. So first DL mixture is converted into the diastereomers. Diastereomers are not mirror images, isn't it? Half a part mirror image, a part not. So you can have a separation because physical properties are differing, like boiling point, melting point, and see that which point is differing. If the boiling point is different, you can distill out. One comes at lower temperature, the other one distills later. So like that, you have to select that physical point and then separate it, and then after that you convert into the DL. For example, I give one example. I have a D lactic acid as well as a L lactic acid. Okay, D acid and the L acid. This mixture is treated with a plus one base, a base which is a naturally available. Most of the plants which gives the alkaloids which contain chiral carbons, more than one will be there, but net optical activity will be there. So a positive, let us say a codeine or thebaine is added. Now what happens, this is a narcotic drug, but still it has got optical activity, and so like that one of that narcotic that is alkaloid is added, it is a plus is added, that means dextro compound D-thebaine is added. It is a base, actually D base, it is a D base, and so therefore D acid will react with the D base and forms a salt. Similarly, the L acid also react with the D base. So we have a L acid and attach it to the D base. Now if you carefully examine these two salts, salt 1 and salt 2, the salt 1 is not totally mirror image. Half part is mirror image, half part is same. This is the other half, upper half is a mirror image, lower half is same, D base, D base. So the relationship now will become the salt 1 and salt 2 are the diastereomers. Therefore, you can separate them by using the suitable physical method. So separation can be done because salt 1, salt 2 relation is diastereomers. These two are diastereomers. Therefore, remember that diastereomers will not have the same physical properties, whereas enantiomers will have the same property. Therefore, in the form of, so I have taken an enantiomer set, a set of enantiomers are converted into a set of diastereomers, and I am separating. So you get the salt 1 and salt 2, other side salt 2. Now hydrolyze it by using some base, like the base is that means when weak base is attached, better add the strong base and hydrolyze it. The strong base is going to react with the D acid, so you will get a sodium salt of the D acid. Instead of the D base salt, sodium salt of the D acid is released, plus that D base will come out. Now you take the sodium salt and get it hydrolyzed with the light acid, so you will get the pure D acid. Similarly, the other side you have to hydrolyze the salt 2 using the strong base like sodium hydroxide, separate that strychnine, codeine or thebaine, some organic bases, you remove it, then hydrolyze it, you will get from this side you are getting the pure L acid. So somehow I am getting the L acid and the D acid in the pure form. So this method is called what? By converting the enantiomers into diastereomers, separate it and then back convert into the enantiomers. So it has no name, in fact, that means method name like Hinsberg or something like that, there is no name. But the method was introduced by the Louis Pasteur, who identified the spoiling of the food material is because of the germs like bacteria, virus and so on. So the one who introduced very old method, but the conceptuality is very wonderful and number of questions are coming. I have a compound, let us say, which is converted into the dextro-levo. So what comes is a racemic mixture. The racemic mixture is treated with a pure either D or L base. If the compounds are acids, I will add base. If the compounds are alcohols, I add a optically active. Same compound should be added to both. This is alcohol, this is alcohol. I add a acid to make the ester. Like that, some connection with the common compound, then you convert into diastereomers and then separate it, then go for the getting the pure D and the L compound. This method is a wonderful method. However, still we are using in several the synthetic compounds to identify, because nowadays the order is, for example, chloramphenicol is an optically active compound which is a very good antibacterial, but it's when prepared you get mixture. If the mixture is taken, one is acting as an antibiotic, but the second one will have some adverse effects, or it is not working or adverse. If not working also, definitely we have to filter it and remove it from the body. It's a job for the kidney and all that. So therefore, now it is punishable when only one D is acting. If you mix the L or giving in the form of dextro is not allowed as per the drug, the codes and all that. So therefore, one has to go for the purification or this resolution and prepare the which is responsible drug active one. Only that type of the medicine should be supplied, not the just prepare the acid, that is D and mixture, and then prepare a tablet, means it is punishable under the acts. So therefore, nowadays the resolution method is one of the method, and number of questions it is attracting. So this is another word called enantiomeric excess or optical purity. That means, as I said, the racemic mixture contains the equal amounts. Say, let us say one is dominating, for example, 6 grams of one compound, 4 grams of its plus 1 is 6 grams, minus 1 is 4 grams. Then what happens? 4 and 4 cancels, 2 grams are extra, isn't it? So that produces some optical activity. So if you take in a flask and measure the optical activity comes, but that optical activity is not the optical activity of that compound. There are two compounds which are unequal ratio. So that's why after cancelling the equal parts, some extra is there, that extra is coming. So therefore, we should not immediately come to a conclusion that is the optical activity of that compound. It is a mixture, unequal mixture is there. Whenever such unequal mixture is there, some optical activity, net optical activity will be coming out. That is called what? Enantiomeric excess or optical purity. That means how much, let us say one compound in out of 100 grams, 60 grams are X compound, 40 grams of Y compound. So this is made up of with 40 plus 20, isn't it? This 40 cancel. This 20 will become the excess of that X compound. The 20 is called what? Enantiomer excess. One of the isomer 20 grams extra is there than the other compound. 40, this is 60 is nothing but the 40 and 20. So 40 equal. If I take 40 and 40, you could have get a racemic mixture. But I have taken one compound 20 extra. So in 100 grams, out of 100 grams, one is 60, one is 40 if I mention. 20 is called enantiomeric excess. The meaning of the enantiomeric excess is moles of one isomer minus moles of other isomer. That is the difference with reference to the total moles and 100. That is the ratio multiplied by the 100. We are getting this optical purity or the enantiomeric excess. If only one compound is, it is called optical purity will be 100, because it is the only one compound. So, total 100 by 100 into 100 will be 100. So, optical purity should be 100. That means no other compound should be there. If the optical purity is going on decreasing, that means 100 becomes 90, 70, 80 and so on. As it decreasing, it is becoming, that is, impurity is more, isn't it? If the optical purity is 100, that is a single compound. That is, this minus that is there, isn't it? So, only one compound is 100, the other one is 0. So, this will become 100. Total moles is 100. 100 by 100 is 1 into 100. Total will become 100. Optical purity, isn't it? Or moles of the one R compound minus moles of S compound. Total moles of R and N. And then the 100. It is not mole fraction, it is the moles I have taken. R can be from the rotation also. Specific rotation or observed specific rotation means after cancelling. After cancelling, one cancels the other one, but some left over. The leftover is called what? Observed specific rotation divided by the specific rotation of the pure isomer. Here, plus or minus is not significant. Either plus or minus, one particular isomer will have the same rotation. So, you take plus or minus, but the value you take need not to worry about the plus or minus. So, observed means after cancellation net comes what? Either plus or minus, again it is not a problem. So, the difference divided by the pure compound optical activity 100 multiplied by 100 will give the enantiomeric excess, or D minus L, D value minus. Here also plus minus is not the significant, whichever the higher one, remove the, that is lower one from the higher one with reference to the total activity. Either D or L you take into 100 will give the enantiomeric excess. There is one problem you see here. Calculate the enantiomeric excess or optical purity of a mixture with 6 grams of plus 2 butanol and 4 grams or minus 2 butanol. This a mixture is there, it is not unequal, isn't it? So, 6 and 4 unequal ratio. So, this 6 grams 4 grams mixture is not racemic mixture, it shows some optical activity. What is that activity is also I am asking. Specific rotation of the pure one is given, and he is asking to calculate this one and also the mixture optical activity, isn't it? Observed optical activity also you can calculate, provided first you calculate the EE. So, EE is equals to, we have already equation here. So, that is the total grams, instead of moles I can take the grams. 6 minus 4 with reference to the total grams are 10 grams into 100. So, this will become the 2 by 10 100. So, that is 20. So, 20 is the enantiomeric excess. The question can be extended. Calculate also the observed rotation. What is the observed rotation for a mixture, this particular mixture? What is the observed rotation? If a pure compound has a plus 35, that means enantiomeric excess already given as a 20 we calculated. This equation serves well. 20 is equals to observed rotation. Observed rotation is the question now, divided by the specific rotation pure isomer is given, that is 13.5 into 100. So, the equation is now observed rotation is equals to, right, 20 into 13.5 divided by the 100. So, that is 2 zeros, if you cancel you will get the 2.7. So, this is what observed rotation, that means more this 2.7 will be the excess, positive one is excess, therefore, you will get the plus which is excess, based on that the sign will be decided. So, that is the 6 grams is positive one, so that value is plus. If this is more, let us say this is minus, this plus, I have to say that minus value. So, therefore, excess one will show its net optical activity, therefore, plus 1 is 6 grams, therefore, the value will be the positive value, otherwise it will be negative value. So, net a mixture containing these two will show the plus 2.3 the observed rotation, and whenever that is 13.5 is its individual, the pure isomer will have. This is called what? Optical purity or the the enantiomeric excess. So, let us have a next feature. There are some optically active compounds. Without a chiral carbon. There is no chiral carbon. There is no chiral carbon, but still the compound shows optical activity. As we have already noticed that there is one compound, there is a chiral carbon, there is another chiral carbon, but because of the compensation, there is a, this is another peculiar example where chiral carbons are there, but still optical activity of this compound is 0. Like that, there are number of compounds, there is no chiral carbon, but still shows optical activity. What is the criterion of the optical activity? It is the, generally we have a carbon with ABCD, okay, this is the first example, but not necessarily carbon. You can have other than carbon, like for example sulfur, which also provides a ABCD groups. Silicon will have this provision, beryllium will have a provision, tetrahedral symmetry must be prevailed. Some double bonds also allowed, but tetrahedral symmetry will be prevailed. A phosphorus will allow, and so on. Wherever this type of the tetrahedral nature, if it is there, compound shows optical isomerism. There are some compounds with cobalt with this is octahedral symmetry. If one is a cis compound like this is En, the other one if it is like this, the leftover groups, that is NH2, 3 and NH3, a cis-bis type of ethylene diamine. This compound you cannot cut into two halves. If the two ethylene diamines are half, this is a cis compound. If the trans compound is like this, cobalt with the two opposite sides, that means ammonia and apponia is opposite, and the two ethylene diamine, that is a divalent one, making the trans is optical activity 0, because it can be cut into two halves. The cis one is optical activity is optically active, and it gives a one dextro compound. Its mirror image is levo compound. Mirror image is possible, that shows. Where is the chiral carbon? Not necessary. So, therefore, chiral carbon is not necessary, the molecule should be chiral. What exactly? Here the carbon is not chiral, but the silicon is chiral. Element may be chiral, like even nitrogen. Nitrogen usually will have a R1, R2, R3, let us say, a lone pair. With this lone pair, you cannot cut into two halves actually. So, this compound is definitely optically active, but it has one small mistake. What is that? It goes on changes, not resonates. The lone pair comes this side, and the three groups will go that side. So, if at all this is a plus compound, its mirror image will be the minus compound, and the plus and goes on equilibrium, and this is called a dynamic equilibrium. A dynamic equilibrium comes whose optical activity will be 0. So, you cannot prepare a pure compound. Even the moment you prepare plus compound, it undergoes flipping. This is called flipping. Because of the flipping, one changes. The center is optically active, but it gives the other one. So, tertiary amines having R1, R2, R3, one group may be hydrogen even, and including lone pair, it is considered as optically active, but it gives the other isomer which is in mixture, therefore. But when you add, let us say R1, R2, R3, R4Cl is added, then the nitrogen will have the four groups now, R1, R2, R3, R4 also, four alkyl groups with a positive nature. Outside the Cl minus will be there. This salt is optically active because the nitrogen is now a chiral center. So, it is not chiral carbon, but any element which is having the A tetrahedral symmetry with 4 sides, 4 groups, unequal groups is going to produce the optical activity. So, one criteria is not the carbon, but any other element. Here we are seeing the compound, there is no particular element with chirality, but it is substituted in such a way unsymmetrically, therefore it is producing. We will see at the end what are the exactly symmetry elements required to show the optical activity later part. But now we have some examples even from inorganic compounds showing this type of the optically active. We have a number of organic compounds that also shows optical activity. There are some examples from the organic compounds also. When 2 double bonds are accumulated like this, the system with 2 hydrogens is called alene. But if it is substituted like 1 methyl, 1 hydrogen, 1 methyl and hydrogen. Now this compound shows optical isomerism because of the reason the plane of this, that is hydrogen methyl in one plane, the double bond will be in another plane. This plane is perpendicular to this one. Now again this plane will be the perpendicular to this plane, and now this the methyl will be a perpendicular one. So finally what happens, this hydrogen methyl carbon and the hydrogen carbon methyl both are perpendicular. Just like a carbon has the 4 groups, these 2 will be in one plane, these 2 will be in another plane. This plane and this plane are perpendicular. That's why when carbon has 4 groups, it cannot be bisected or has no plane of symmetry, therefore it is going to show the optical isomerism. The same reason here, a carbon having the 1 double bond is eligible to the ABCD if you have geometric isomerism. A carbon is having 2 bonds, that is 1 bond attached with 2 bonds. Now here you need not to have ABCD, you can have AB also eligible because it is not a regular tetrahedron. With 1 carbon it needs ABCD definitely. The repetition of groups will not give optical inactivity, but non-repetition is going to give the optical activity. Here you can have a repetition AB because it is not a regular one, it is a elongated tetrahedron, therefore AB. 1 methyl hydrogen is optically active. Okay. So no double bond or 2 double bonds, 0 double bond, 2 double bonds. Similarly 4 double bonds, 6 double bonds, all even number of double bonds attached, accumulated enes, dienes or tetraenes, hexaenes, and all even numbered accumulated, that must be, not conjugated. Accumulated enes with AB are going to show optical isomerism. Whereas 1 double bond, okay, 3 double bonds, this and this will be in the same plane. So therefore when you have a AB, you can have a AB or AC or CD. You can have a ABCD, you can have a ABAB or ABAC. One is not repeated, both are not repeated. All this shows the geometric isomerism. That is, odd number of cumulated dienes are showing geometric isomerism. Even number, including starting from the no double bond, 2 double bond, 4 double bond, 6 double bonds, are going to show the geometric isomerism. These are called alenes. Without these groups is called alene. So alenes are going to show the optical isomerism. It's a mirror image. One, you have to write the mirror image. You put a mirror and the mirror how it looks, you have to write the other isomer, and that and this together is called a racemic, that is an enantiomeric pair. You can also have a cyclo compounds. For example, a cyclohexane, imagine for some extent you consider this as a plane, and there is another cyclohexane attached to this one. Definitely if this plane is in this one, the other plane is perpendicular to this one. Isn't it? Just like a carbon has 4 groups, this carbon is called a spirocarbon. So the 2 rings are perpendicular to each other. If here I have a methyl and hydrogen, if here I have a methyl and hydrogen, this compound is going to show optical isomerism. Okay, they are called spiro compounds, but substitution should be there. Both are carbons or both are hydrogens, means no one difference in the groups. Now these two also will be perpendicular, therefore it is going to generate one double bond and one ring, also going to show AB and AB type of the substitutions are going to, this is exocyclic double bond containing cycloalkanes are going to show optical isomerism. So two double bonds are to this one, or one double bond, one this one. You can also have some two benzene rings. Actually, when two benzene rings are attached like this is called biphenyls. These two biphenyls would like to, can have the opposite symmetry also, but generally when they are in conjugated, they come to into a same plane, so that the resonance is extended. Both are aromatic perfectly, but still the resonance can be entered into other ring, therefore extended conjugation benefit. The two rings are observed to be in the same plane. But however, if the groups are like this, R1, R2, and the groups on the other system should be either repeated or another type, R3, R4. Now what happens? These two, because this is almost attached, the carbon, this is alkyl 1 and alkyl 3 will have a repulsion. Due to the repulsion, the plane of the benzene, so this will be in one plane, this will be in the other plane. So one you write ordinarily, the other one you write little bold type, so that you can understand this is back side, this is coming out of this. This is in the board plane. Here half is in the board plane, this is half is coming your side, half is going that side. So the two planes will be perpendicular now, because of the two groups touching each other, it rotates. So the two benzene rings planes are perpendicular to each other. So therefore this molecule also loses the symmetry. So you cannot cut fundamentally into the two halves. Therefore this compound has no symmetry element, therefore it is optically active. But biphenyls should be on the ortho positions only. If the groups are backside, or two are front and two are back, not they going to show this type of isomer. So huge number of compounds where the primary idea is, in one way you can say, if you cannot cut into two halves, the compound is going to show the optical isomerism. Actually symmetry elements, if you take up details, we'll take that later, but that is that is not necessary to have a chiral carbon. The compound should be chiral, not the chiral carbon or the chiral nitrogen. The element is not necessary, but the molecule should be in such a way it is asymmetric. Then the compounds are going to show the optical isomerism.